Yeah, thanks everyone for coming. Um, it is my great honor and privilege to talk about my colleague's work today, Anna. Um, so there's two Anna papers Alexei was mentioning in the Slack. There was the original Anna paper, which was from 2019, and this paper talks about like what is Anna, and then the paper that was assigned for today, which is the Autoscaling 2020 paper. So I'm going to actually talk about both papers. The first paper is kind of a background section of the second paper, but I'm going to talk briefly about both because I think understanding the auto scaling is a little easier when you understand like what Anna is. So there'll be two parts of the talk essentially. Part one is going to be what is Anna, and part two is going to be, how do you auto scale it? All right, but before we go into any part one or part two, I'm going to start with a little mathematical background on lattices since they play such an important part in Anna and because it's fun to talk about. All right, so if you're like familiar with CRDTs or something, this is probably very elementary for you and you've already seen this before, so my apologies, but we'll go through it kind of quickly. All right, so lattices. What is a lattice? A lattice is a set S along with a binary operator, which I'll call join, which takes in two things in S and poops out one thing in S. I call this join, such that three things are going to hold. First, join is commutative, which is to say that A join B is equal to B join A. Second is it's associative, which is to say that A join B and then join C is the same as joining B and C first, and then A. And the third is that it's idempotent, which means that A join A is equal to A. All right, so lattice is just a set with some operator you can use to combine things. It's commutative, associative, and idempotent. And then we have this thing called a least element. A least element, I'll say this is pronounced bottom or bot. Is such that it's some element in S such that A join bot is equal to A for all A. I'm not doing all the quantifiers, but hopefully it's obvious what I mean. All right, so we can look at some examples. The simplest example is probably integers, or no, I should say natural numbers under max. All right, so what I mean is that the set S is a set of natural numbers, and max is the join operator. And we can quickly convince ourselves that it's associative, commutative, and idempotent. Associative essentially means that if I take the max of any number, A with the max of B and C, that's going to be the same as if I do the max of A and B and then C. Hopefully it's obvious that's true. Commutative, this should also hopefully be obvious, that it doesn't really matter what order we take the max in, and idempotent, obviously the max of something with itself is itself. And the least element here is 0. Because the max of 0 and anything else is the something else. All right, so that's a very simple example. There's a couple other examples that are pretty simple. So we have sets under union. So I consider the set of all sets and the join operators unioning them together. Hopefully that's also obvious. It's associative, commutative, idempotent. The empty set will be the least element. And then we have some slightly more interesting ones. So for example, pairs of lattices. So if you give me two lattices, I can hand you back a new lattice, and my lattice is simply pairs of your lattice. All right, so we'll say pairs of lattices, A, B, where my join operator takes in two pairs, so A1, B1, and I join it with some other pair, A2, B2, And this is just going to be a pairwise join. So it's going to be A1 joined with A2 using the join operator from A, and then B1 join B2 with the join operator from B. All right, so we can actually compose lattices. And then the lattice that's maybe most relevant to Anna is this, let me say, last writer wins lattice. Last writer wins. And the last writer wins lattice consists of pairs of the form t, where t is some time, so some integer or something, and then some lattice value. Let me do lowercase a. And the way I join two lattices, TA join UB, is going to be TA. If t is bigger than u, it's going to be UB. If u is bigger than t, and it's going to be T A join B if t is equal to u. So this is a pair lattice thing going on, right? I talked about the pair lattice. This is like a pair of integers and a pair of, well, it kind of is, not really. But I have timestamps and I have some lattice value. And essentially, when I go to merge two things, the one with the higher timestamp is going to win. If they have the same timestamp, then I just merge together the elements. So there's like a last writer wins. The highest timestamp pair is always going to dominate in the merge. Okay, any questions so far on lattices? So far, mostly just background, I think. Okay. All right, so why are lattices so cool? Well, this is sort of like the CRDT kind of stuff coming in. We're going to have a key property. What do lattices give us? Well, let's consider I have some set of numbers, and we're going to merge them at our max. So let the join be max. So let's say I have numbers 3, 1, 2, and 4. And I'm going to merge these guys together. So the max of all of these guys, and obviously I get 4. Okay, but now let's say I'm going to shuffle up this list, and I'm going to maybe duplicate some numbers. So I'm going to go with 1, then 4, then 3, and 1, then 2. All right, so I've shuffled them all up, and I've duplicated 1. And then let me take the max. So I'll take the join again. But we still get 4. All right, so if I have a lattice, because the join operator is associative, commutative, and idempotent, I can take any set of stuff, mix them up in any order, duplicate as much as I want, and if I just merge them all at the end of the day, I'll always get the same result. All right, so that property is going to sort of be the thing in Anna, which makes sure that all the replicas converge. We're going to see if, as long as everybody sort of gets everything, it doesn't matter if there's duplicates, doesn't matter if there's reordering, as long as they always take the merge, they're always going to end up in the same state. Okay. So with that, let's move on to Anna. Part 1, what is Anna? Okay, so I'll give a high-level description of the system, and then I'll give an example of how it runs. Okay, so Anna is a key value store. Oops. The key value store where the values are lattices. That's sort of the big thing. This is a key value store, but the values are going to be lattices. It is, oops, it is not strongly consistent. So that's going to be a big part of the story. Not strongly consistent. And that's by design. And because it's not strongly consistent, we're going to be able to go very fast. So it's very fast. It's also sharded and replicated. And what else? Shared nothing. Okay, so I think these are the most important descriptors of the system. Some key value store that's not strongly consistent, super fast, sharded, replicated, and shared nothing. All right, so now let's look at an example. Thankfully, Anna is a very simple system by design. I think the simplest things tend to be the fastest, which means that it won't be too hard for us to understand the system pretty much in full. Okay, so let's look at an example with one shard. The Anna is multiple, it is sharded, so we can have multiple shards, but just to keep the example simple, we'll have one shard. Okay, so I'm gonna have 3 replicas. And every replica is gonna have a key value store, right? Remember, we're a key value store. Where X, actually no, let me say, well, let me not do XY. Let we have K, and we have V. And I'll have 3 things, X, Y, and Z. And V here is a lattice. And so let's say that the values here are natural numbers with max. And initially, we start the database off with the least element, 0. And in addition to the key value store, all of these nodes are also going to have some set of dirty keys. All right, so all the replicas are going to have a copy of this. Oops. Hopefully this fits. Okay. Like this. Okay. So now let's see how the protocol runs. When I'm a client and I want to, so I'm going to support sets and gets, right? I'm a key value store. When I set a value for some key, I send it to any replica. Any replica that has that key. Remember, we're sharded, but here there's only one shard. So here I'm just going to send it to any replica. So maybe this first client wants to set X to 2. Well, in a normal key value store, right, if I get a set to some key, I'm going to override my value with the new set. With ANA, since everything is lattice-based, instead, I'm going to merge in the value into my value. I'm going to merge the setted value into my value. So here, I'm going to replace 0. I'm not just going to replace it with 2. I'm going to replace it with the merge, or the max, of 2 and 0, which happens to be 2. Maybe later, some other, and crucially, we're also going to say now that X is dirty. All right, so the dirty set just says, what are all the keys that I've modified? All right, maybe this other client contacts the third replica and says set X to 4. It'll change 0 to 4, mark X dirty. Maybe it says set Y to 2. We'll change Y to 2 and say Y is dirty. Okay, so send to any replica, doesn't matter. They're going to merge in the value. But replicas are not the same, right? So we need to make sure they converge. So what happens is every so often, these replicas are going to gossip. They're going to broadcast their dirty keys, the values of all the dirty keys, to the other replicas. So every so often, for example, this top guy is going to send to the other 2 replicas and say, hey, my key X is dirty, so I'm going to send you X and 2. And then it will eliminate X from the dirty set. And when these 2 other replicas get this, they're going to merge it in. So the second replica will replace 0 with 2, because 2 is the max of 0 and 2. And the third guy will replace 4 with 4, because 4 is the max of 2 and 4. All right. And one of the properties of ANA is that these replicas, maybe these 2 guys are on 2 machines, 2 completely different machines, or they are maybe just 2 threads on the same machine. So in ANA, every thread is completely independent of one another. Every thread has its own replica. All the replicas do this gossiping. Clients can send to any replica. And that's pretty much it. That's the entirety of ANA. If you understand this, you pretty much understand the whole system. Are there any questions on this, on just how ANA runs? No, okay. I hope that's because it's clear. All right. So another thing to understand about ANA, though I'm not going to spend too much time on it, is how consistency works.
Hey, Michael, we do have a question in chat.
Oh, I'm sorry. Does dirty wait for ACK? Ah, yes. So you said when a replica sends its dirty stuff to the other nodes, does it wait for an ACK? I'm actually not sure, but I'm guessing it should. I'd have to check the paper, though. That's a great question. Actually, maybe it doesn't. Well, we have to see. I wouldn't be surprised if it did, but I have to check the paper. So I think that, so sorry, I should clarify the question. So I think the question is, when I'm this first replica and I'm sending my dirty keys to the other replicas, do I immediately eliminate the key from my dirty set, or do I wait for the other replicas to acknowledge me and say, okay, I got it, before I clear it from the dirty set? And I think the idea here is that if I send out my dirty keys, but all those messages get dropped, then I have some update that these other guys don't have. Jonas thinks that it gossips the change value, so I don't think so. Yeah, I'm not sure. I mean, it would definitely affect what consistency claims you can make. If you don't wait for X, if I'm replica 1 and I get a set to X, and I update my key, I gossip it, those gossips drop, and no one ever writes to X, then I'm not eventually consistent because I'll always be divergent. And I'm not sure if they gossip keys that aren't dirty. So I'm not sure. But either way, I think you can sort of understand the ramifications. So I think it's just a design decision. Also, does the dirty communicate with a timestamp? Yeah, so great question. So right now, all Anna has is keys and values. Okay, so I've described things in terms of these abstract values. There's no timestamps yet. And this is how the protocol runs. So whatever this is correct. What we're going to see is that if I choose particular lattice values for my values, then I can do things like introduce timestamps, do last writer wins, maybe get causal consistency, and so on. So the timestamp stuff is going to depend on which lattices I choose. If I chose integers with max like here, no, there would be no timestamps. That's a great question. All right.
And the last question, I guess. And in Anna, you can choose any lattice for your values? Or
yeah.
So it's much wider than the eventual consistency model that is used in Cassandra, for example.
Exactly, yeah. So the cool thing about Anna is that because we get to plug in any lattice we want, we could choose integers with max, we could have sets with union, we can do timestamps, we can do some vector clock stuff. We can change the sort of consistency level of the system without having to change the system. We just change the lattice. So it's sort of this like pluggable thing. And depending on which lattice I choose, that is going to determine what consistency I get. That's a great question. So yeah, I'm actually not going to get into it too much because this isn't quite as relevant to the auto-scaling stuff. But I'll just write it out. So yes, the consistency level depends on the lattice, on what lattice we choose. And in the paper, they talk about, for example, last writer wins. I think that's the default. They also talk about causal consistency. They talk about read committed, and they talk about some other ones as well. So by choosing very clever lattices, I'm going to get different consistency levels. But I'm not going to dwell on it too much. Like I said, it's not as relevant for the auto-scaling. But the system itself is. Okay, any last questions before I move on to the auto-scaling stuff?
I just wanted to add that this acknowledge for dirty values depends on the consistency level, at least in the case of Cassandra. Okay,
that makes sense. So you're saying whether or not I act is going to affect the consistency level?
There you can choose for what number of replicas you wait before returning their response to the client.
Okay, yeah. So if I understand Anna correctly, one thing here is that I should have, sorry, that's a great point. I didn't make this clear. I think that replicas respond to clients immediately, and they do the gossip, what's the word? Like asynchronously, offline. So they're not actually waiting for access to respond to the client. So in Cassandra, if you're saying that I think that like I do my write and I have to wait for it to propagate to a certain number before I respond, it's a little different, I think. All right, auto-scaling. Let's chug along. How am I doing on time? Maybe I need to go a little faster. All right, part 2, auto-scaling. So this is where things start to get a little complicated. So I am going to try to explain this in terms of a slight simplification. So I won't have time to get through all of the complexities, I think, of the problem, but hopefully I can get through enough that it sort of, I don't know, lets us understand the heart of things. So let me paste this in. Paste. No, that's not what I want. Paste. No, why is it doing this? Okay. Well, yellow. I'll just draw it again. Okay. So I'm going to use these little diagrams, and I have to explain what they mean. Okay, so this thing, let me choose a different color here. 1, 2, 3, 4. 1, 2, Okay. So this little box is going to represent a replica. Oops. 1, 2, 3, 4, 5, 6, 7, 8. So this is some replica, replica 1. So this box is a machine, okay? It represents a machine. On the y-axis here, this represents the number of keys that the machine can store. Okay, so here, this machine, this replica, can store 3 keys. It only has enough space for 3 keys. And on the y-axis here, oops, this represents the commands per second that the machine can tolerate. All right, so this means that this replica can service 8 requests per second. All right, it can't do more. It can't do like 100 requests per second. So I can store 3 things and I can service 8 requests per second. Okay, so then let's look what happens when we have a certain client load. All right, so let's say that a client shows up and it says, okay, I want to write to X and I have a load of 4 commands per second. Then this replica can service that without a problem. Actually, I'm going to copy this also before I mess it up. All right, so this replica can service X, no problem. It says I'll store X and I'll fill in 4 of these boxes. And then let's say another client shows up and says, okay, well, I want to write to Y and I have a load of 2 requests per second. This box is this box says sure, no problem. Okay, so I'm filling up horizontally the throughput, but then I'm also filling up the storage vertically. Okay, now there's 2 situations that can happen, which are going to maybe make me have to increase the number of machines. All right, so there's going to be a couple scenarios. Situation 1 is not enough space. Actually, before I move on, is this clear? Because if this little abstraction is not clear, nothing's going to make sense. Does it make sense that I have like this storage throughput thing and clients are like exhibiting load and I'm placing the load in these little boxes?
Yeah, this is working for me at least.
Okay, okay, good. If it's a little unclear, maybe as I go on, it'll start to get more clear. Okay, so there's going to be 2 scenarios that I want to talk about. Let's see if I can duplicate this. Okay, perfect. Okay, scenario 1, situation 1, I don't have enough space. So let's say another client shows up and he says, okay, I want to store Z and I want to do 1 request per second. So I say, no problem, I'll do Z. And then somebody else shows up and they say, okay, well, I want to store A and I also have 1 request per second. Well, now we don't have enough space. My machine only has space for 3 keys and all of a sudden I have to start servicing 4 keys. So I just don't have enough space, right? I can't put A here, there's no space. So what I have to do if I don't have enough space is I have to add more replicas. So this was replica 1. I'm going to have to add a second replica, replica 2. And on this replica, I have enough space to store A. So I would store A here, 1 request per second. Okay, hopefully this is pretty obvious. Every machine only can store so much stuff. If I have more keys than I have space, I have to add more machines. Okay, so that's one scenario, not enough space. That's possible. There's another possible scenario, which is not enough CPU. Scenario 2, not enough CPU. Okay, so the story here now, let me erase all this. So imagine now, I'm going to come to you. So we only have 1 replica, and I'm a client, and I'm going to show up with key Z, and I want 4 commands per second. Well, this machine, this replica, can only process 8 things per second, and now I'm trying to give it a load of 10. Right? So I could try to put Z in here, but it won't fit. So what am I going to do? I have to get another machine, right? This is the second scenario. If I have another machine, then I can offload Z to this machine. No problem. Okay, so if I either have too many keys or I have too much load, I have to get another machine. Well, there's a third situation that can happen where I'm able to handle some load without having to necessarily get more machines. And that is moving hotkeys around. All right, so scenario 3 is hotkeys. Oops. All right, so now what have I concocted here? So now let's say that I have, okay. So let's say I have 2 replicas and I have load of 4 on X and 2 on Y. And I put X on the first replica and Y on the second. And then what happens is that my key X gets hot. So instead of a load of 4, all of a sudden X gets a load of 10. All right, so if I try to put all the load on the first replica, which is the one that has X, I won't have enough. I won't have enough CPU. Which means that what I have to do is replicate this key X between 2 servers. So I'm gonna put X on replica 1 and on replica 2. And if you remember with Anna, I told you that if I have some keys stored on multiple replicas, clients can send to any of them. So I can load balance the load. If I had some strong consistency, I think Alexei was talking about this in Slack. If I have something like Paxos, for example, adding more nodes is not just going to all of a sudden make my load like be able to distribute between them. But because Anna is not strongly consistent, and because it lets us have clients send to any replica, I can replicate a key and decrease the load per machine. So here, for example, if I replicate X on 2 machines, then I can split the load 5 and 5 each. You can imagine that the key might get even hotter. Maybe I go X to 20. And in this situation, now I would have to get another machine. This is situation 2 above. Okay, any questions on these 3 scenarios? Either I don't have enough space, I don't have enough CPU, or I have to do some, I have to replicate some keys, some hotkeys in order to make sure I can fit in the CPU. Any questions on this? No, okay. I also hope it's clear that replicating a key will never help with storage, right? That makes storage worse. So this whole replicating thing is only for CPU. It wouldn't work for keys. It would make things worse. Okay, so if you understand these 3 scenarios, then you can understand 3 of the main mechanisms in Anna. The 3 mechanisms in Anna, well, 3 of the mechanisms in Anna handle these 3 scenarios. Okay, so situation 1. In Anna, there are these 2 parameters, S upper and S lower. And these are these measure total like space usage. So if we look at our system and our space usage is more than S upper, maybe S upper is like, I don't know, we're using 60 gigs or something. If we're using more than 60 gigs, then we need to add more machines because our machines only have a certain like 61 gigs or something. So if I fall above S upper, then I'm going to add more machines. And this corresponds to not enough space. This is situation 1. If my total memory usage is below this, then I remove machines. Saying I have no issue with the space. I have too much space. Mechanism 2 is going to be similar but a little more complicated. This is going to correspond to not enough CPU. So how do I measure not enough CPU? Well, at this point, I have to tell you that my model is sort of idealized. In the real world, right, if I have a server and it can only handle 100,000 requests per second, and I give it more than 100,000 requests per second, it will still sort of churn through all the requests. It's just that the latencies of all the requests is going to start to rise, right? I'll hit my peak throughput, and then my latencies will start to skyrocket. So we can measure overloaded machines by looking at latencies of requests. And in Anna, we're going to specify some latency SLO. So I'm going to say, okay, I want all my requests to be 5 milliseconds or lower. And the system is going to have this, this threshold that says, okay, if my latency, the latencies of my requests, if it's greater than some fraction F upper of my SLO, and my CPU usage is greater than this threshold C upper, then I will add more machines. So this is just a way of saying too much load. not enough CPU, I need to add more. And the opposite, I'm not going to write it. It's going to be the flipped. Latency is less than F lower times SL low, and CPU is less than C lower. All right, so this just corresponds to not enough CPU or too much CPU. And the third situation, the third mechanism, is that every t seconds, I'm going to make this little histogram for every key, what's the access frequency? So I'll look at every key. So maybe I have key X, I have key Y, and I have key Z. X is not touched that much, Y is touched a little bit more, and Z is touched quite a lot. Well, we're gonna have these two thresholds. The first is called H. Oops. And H says, okay, if my access frequency is above H, then that key must be hot. So I'm going to replicate the key on more machines. If my thing falls below L, then my key used to be hot, but it's not hot anymore. So I'm going to unreplicate it. I'm going to sort of consolidate my memory. So H and L handles our third situation of having to replicate and unreplicate hot keys. Okay, any question on the three situations and how these three mechanisms address those three situations?
All good.
Yep. Making sense. Yeah.
Okay, perfect. Yeah, hopefully so far, yeah, it seems straightforward. Okay, so last thing, this is actually the juicy part, and I'm actually not going to dive into it, partially because I think it would take too long, and partially because I myself am not fully grasped this. But I think the interesting stuff comes in when we start talking about different numbers of machines, different types of machines rather. So far I've showed this trade-off between space and CPU. Now we're going to see additional trade-offs in terms of money and in terms of oh, I see. Jonas, you have a question. Are the rules on a per node level or per system level? Yeah, great question. So I think that S upper and S lower are on a per tier level. So you remember there's some nodes in the memory tier and some nodes in the disk tier. I think for each tier individually, we'll look at the storage and either add or remove machines in that type. I think. I could be wrong. The latency, I think, only affects the memory tier, if I'm remembering correctly. And situation 3 is on a system level, because this is determining, oh no, yeah. There's some other stuff, for example, when do I promote from one tier to another? So that's sort of across tiers. But you only replicate in the memory tier. You only increase replication in the memory tier. Anyway, long story short, it's either per tier or kind of across tiers. Yeah, not per node. All right. And the mechanisms by which they know all of these statistics and stuff, I'm not talking about also. So you just assume that I know all these things. Okay. The problem gets much more complicated when we start looking at different types of machines. Now the trade-off space is going to get very complicated. Okay, so far I've shown you this machine. I'll call this a memory machine. And let's say that this machine costs $3 per hour. Well, we have this other EBS tier, which I have been ignoring so far. And this one, let's assume it doesn't have quite as much throughput. Oh no, I want to have 4. But it can store more stuff. So this one is like reading and writing to disk, so it can store more stuff, but it's a little slower. And let's say that this EBS one costs me $2 an hour. All right, and let's say I have the following load. I have A, B, C, D, E, F, G, H. I have a load of 6 on A, 4 on B, 2 on C, 1 on E, and then none at the moment for E, F, G, or H. And my question to you, we can spend some time thinking about it, or I can also just say the answer is, what is the cheapest way to fit this load? So essentially, you walk into the store, and I have two models for you. I have the memory model, and I have the EBS model. And the memory one is this long, sort of short guy, and EBS one is tall and skinny. And you have this load, and I have to fit this load onto the machines, and I have to make a choice of how many of each machine am I going to buy, and then how am I going to replicate and assign keys to different machines to fit. So if people want to take or actually before, is it question the setup? Is it clear the setup? Like what the problem is of I have to pick the right number of machines and put keys on different machines? Okay, I assume it is. So maybe spend like a minute or two trying to think to yourself what the cheapest way to do it is, and then I'll show you the answer. And if you know it, feel free to post it in chat or something.
1-on-1.
Ah, 1-on-1. Okay, Alexa, you might have outsmarted me. I think that that's not doable, but I could be wrong. Do you have a proposed way to split up the keys?
It's not doable. I miscounted my
Okay.
arithmetic is I guess at the first grade level.
That's okay. Yeah, 1-on-1. I don't
2 of memory, 1 of EBS.
2 of memory, 1 of EBS. Okay, great answer. 2 memory, 1 EBS. So let's do it. Let me copy this. Hopefully this is fun to people. This is fun to me at least. All right. So, oh no, 2 memory, sorry. 2 memory. 1 EBS. Oops, what is this? Okay, let me copy my load. Okay. So here we can definitely go A6, 2, 4, 5, 6. We can go B4, 1, 2, 3, 4. We can go C2, 1, 2. We can go D1, why not? And then we could do maybe E, F, G, H. So that definitely fits. And the cost is going to be $3 plus $2 plus $2. So that's a total of what? Oh no, I'm sorry. $3, $3, $2. That's $8 total. But is that the cheapest? This definitely works, but is there a cheaper?
The cheapest if we will put everything into the EBS. Without.
Okay. The cheapest is all EBS. Okay, let's try that. I hope I tried to construct it so that that actually wasn't right, but I might have messed that up, but let's see. Okay, so I have 8. So actually, I'm not going to draw it out. I can do some quick math here. So I have total of 6 plus 4, which is 10, 12. I have 13 units of load, and each EBS is going to have at most 4. So I'm going to need at least 4, 8, 12. I'm going to need at least, yeah, I'm going to need at least 4 EBS, right? Wait, hold on. My total load is 13, 4, 8, 12. Yeah, I'm going to need at least 4 EBS then to saturate the load. And 4 EBS is going to cost me also $8. So it'll be as expensive. There's actually a cheaper way. And the cheaper way is going to turn out to be 2 EBS and 1 memory. It will end up fitting. I'm just going to show you so I don't have to draw it.
But you can't put only the A into the single row in the EBS, right? I mean, the A is 6 and the EBS throughput is 4.
Yeah.
Or I'm missing something. I mean, you can put almost everything besides A into a single EBS, and then put A into a RAM, for example, and then you need only 1 EBS and a single RAM.
So are you saying 2 EBS and 1 memory?
I'm saying 1 EBS and 1 memory.
EBS
you put A in.
EBS only fits 4 requests. So let's say you put B into EBS and that's it. The machine is maxed out. It has more storage, but doesn't have the processing capacity left.
Ah, okay. I missed. Yeah, I missed the point about throughput.
Okay, I'm happy that got cleared up. So yeah, it turns out you can do it with 1 memory, 2 EBS. Here's the drawing to show you that it all fits. And this is $7, I think, as long as I did my math right. I'm also maybe at a 1st grade math level here. So I think this is a total of 7. Okay. the point of this was just to show that this is a complicated set of trade-offs. And I've only even expressed the problem as how do you make it fit at all? But really the trade-offs are more complicated. It's like, given a certain SLO, I want to minimize budget, or given a certain budget, I want to minimize SLO. Like I said, there's the fact that I can actually overload throughput. It'll just come at a cost of latency. And then there's all the things with, well, when I'm transferring keys, that also adds load. That also like complicates things and blah, blah, blah. And I have to replicate things and stuff like that. So Anna, presents one way of doing things. I'm not going to spend time going into the details, but it'll store cold things pretty much replicated in EBS. If it gets hot, it'll move it to the memory, and then it's going to use those heuristics that I talked about to manage it in memory. But this is a super complicated problem, very complicated, I think. And like, if you wanted to get some optimal solution for however you define optimal, it would definitely be challenging, very challenging, I think. But yeah, that's all I had.